In this video, we're going to go over maybe skip through some things, our first unit of trigonometry. This is Math 20-1's version of trigonometry, where half of it is taking what we learned from 10C, our trigonometric ratios, and applying them to new situations like Cartesian planes and oblique triangles. That's triangles that are not right angles. And then the other half is just setting the stage for 30-1. And 30-1 is going to look at a lot of new fancy ways of using trigonometry. So we really want to kind of set ourselves up for it successfully. Anyways, without further ado, our first topic is what's called angles and standard position. I am not going to write down definitions on this because my penmanship is bad and I don't really feel like writing a bunch. So I'm just going to say them, and you use your ears and then your hand, and you can write them. So when we talk about angles, it's helpful to start putting them in terms of how we can measure them using a Cartesian plane. A Cartesian plane, you might remember, has these two axes, our x-axis and our y-axis. These are essentially just number lines that are perpendicular to each other. They are allowing us to kind of denote things in two-dimensional space here. So one of the things that's really helpful for angles is putting them on the Cartesian plane. One important idea that we'll talk about with our Cartesian plane is that it breaks it into four sections when you have these two perpendicular lines, and these are called quadrants. And we use Roman numerals to label our quadrants. So we've got labels 1, 2, 3, 4 for all of our quadrants. And note that they're going not clockwise, but anti-clockwise around. Okay, so we start quadrant 1. This is where we've done most of our work previously. Quadrant 1 is where you expect it to be, and then you go counterclockwise around 1, 2, 3, 4. Okay, so those are our quadrants on our Cartesian plane. So when we talk about an angle on a Cartesian plane, what we're going to do first is we're going to put angles in standard position. So to form an angle on our Cartesian plane, we're going to use two lines or rays, and we're going to call these arms. And between those two arms, we'll form an angle in standard position. The initial arm, the first arm, is always going to be started on our positive x-axis. So in this diagram where it says sketch, which means accurately draw, a 120-degree angle in standard position, we're going to draw our first arm on our positive x-axis. Now, I don't always need you to draw this for me because if you just have the x-axis, right, the line's already there. But the other arm is really important. This is our terminal arm. To draw our terminal arm, what we're going to do is we're going to start where we put our initial arm, or if you don't draw your initial arm, start on the positive x-axis. And you're going to go rotating counterclockwise 120 degrees. When I said an accurate drawing with sketch, I'm not going to pull out a protractor and audit whether or not you're accurate on this. But for 120 degrees, what I'm going to do is I expect it to be in quadrant 2, right? So 90 degrees to get up here, and then another 30 degrees to get roughly there. And then we'll draw our terminal arm, ta-da, like that. So again, just going through our terms, this angle in standard position is 120 degrees, and it's formed by comparing an initial arm, our positive x-axis, with a terminal arm on, 120 degrees worth of rotation around. Okay. Maybe helpful to remember here, right? If you start at 0 degrees, then this is 90 degrees, 180 degrees, 270 degrees, and finally the whole circle is the 360. So remembering those kind of like general points is really, really helpful when you're trying to think about where our angles are going to be in standard position. You've got a lot of practice here. I'm going to skip most of these, but one that actually is helpful to see is this one. So I just finished saying, okay, if you go 360 or the whole way around, how the heck am I going to get 450? Well, the nice thing is, if it's a circle, you can just go 360, and then I need another 90 degrees to get to 450. I can take my angle and I can go continuing around the circle. So it's really helpful for us to have this Cartesian system because it allows us to examine angles or like rotations that are more than that 360 degrees in a way that we can still recognize it. And this like curlicue, this is the proper way of doing it. It might look a little ridiculous, but there's our angle. Let's draw our terminal arms. So I kind of started here, initial arm and then terminal arm. Again, you don't need to draw your initial arm, but you should always draw your terminal arm. And to reiterate, this angle that I've drawn, 450 degrees, that's even more important than drawing your arms. You need to draw this angle, okay? There will be diploma questions yes, 30-1, not even 20-1, that ask you to draw an angle like this, or there could be, right? The written response happens to cover that. So you need to know what that is. Okay, when I do this 450 degrees, it kind of just looks like, well, that's just the same kind of line as if I'd just drawn a 90-degree angle, right? So why not I just look at that? And that's our next idea, which is called a reference angle. Oh, look, you can see someone's already written on this. It's almost like I tried to film this video before. Anyways, so when we talk about reference angles, a reference angle is saying, well, instead of going all the way around the circle for something like this, let's draw an angle here. This is roughly 225 degrees, sure. So in standard position, it looks like this, 225 degrees. What if I wanted to like make a triangle out of this using just this smaller segment here? Let's do line. So here, what if I want to like think about this trigonometry triangles? The easiest triangle to make is just with the nearest x-axis. And so that's actually what reference angles do, is they say, instead of comparing with standard position, starting all the way at the start, let's just look at the nearest axis. So if this is 180 degrees, the negative x-axis, all I need is another positive 45 degrees to get to our line. And so standard position, 225 degrees, matches with a reference angle of 45 degrees. Now, it's really important that when we're talking about these, if I'm using a reference angle, I could also have a 45-degree angle like this, right? Ooh, nice 4, thanks. Or like this. So I could have a lot of 45-degree reference angles where I'm just moving from my nearest x-axis. So I need to make sure I'm also mentioning what quadrant I end up in. So quadrant 3, in this case, a reference angle of 45 degrees in quadrant 3 will have a standard position angle of 225 degrees. I'm not going to draw these for you. You can draw them for yourself. But I guess I'll draw one more. Damn it. So with this one, oh, sorry, don't demonetize my demonetized channel. Okay, so with this, if I have 135 degrees, that puts us right here, 135 degrees. And our reference angle, the notes say always positive values. So even though we're kind of like going clockwise, which is backwards, it's still just 45 degrees as our reference angle, okay? What's special about this angle here is that the triangle it forms is an isosceles triangle. So it forms a triangle that, nice try. It forms a triangle like this, where if this angle is 45 degrees, these two sides are the same. And yeah, like the other angle is also 45 degrees. So it's an isosceles triangle. Okay, so that's kind of neat. It has special qualities that we're going to look at. And that brings us to our next topic. Before we kind of go into this, we need to remember that an exact value is a way that we can represent something like this, the square root of 2. So if I write square root of 2, that is precise. That is an exact value that matches a specific number. But the square root of an imperfect square, you might remember from a couple courses worth of me blabbering about it, is an irrational number, which means it has a non-terminating, non-repeating decimal. So how do I write this number down while still keeping exactly the value that I want? You leave it. Don't try and type it in on your calculator and say, well, I have 12 decimals. That's a lot of precision. No, the only precise way to do this, square root 2. Another example of an irrational number is pi. Pi, you've got a pi button on your calculator. And instead of putting 3.14 like some sort of weirdo, or 3 like an engineer, you can just leave it as pi. That's exact for something that is irrational. Leave it the way it is. So if I ever ask you for an exact value, leave your radicals alone. Okay, I talked about two distinct special triangles in this section, or I will talk about. The first we already did talk about is this one where I have 45 degrees and 45 degrees. The other one is if I take that 90 degree and I cut it into two parts, so a 30, 60, 90 triangle. Oops, and obviously that's a right angle as well. So here are your two special triangles, the 45, 45, 90 and the 30, 60, 90. And these are, of course, measurements in degree. I'm not going to write the degrees. With these, one of the things we talked about in Math 10C is that any triangle or any angle that has the same measurement due to proportionality must have the same scale proportions to its sides. And so with a 45 degree angle, you'll always have a triangle like this that's isosceles. And so you'll always have similar triangles when you have these angles. Likewise for 30, 60, 90. And so one thing we're going to do in this section is memorize the ratios for these two kinds of triangles. And that's helpful because it actually, if you know two triangles, you know the ratios for three angles, 30, 45, and 60. So starting with this one, I'm going to keep it simple. We're going to say, let's call this side length 1. It's an isosceles triangle, so if this is 1, so is this. Our missing side here, well, we can just use the Pythagorean theorem. I'm leaving room so that you can do the Pythagorean theorem here. I'm just going to tell you that this side is 2. But not 2, sorry, the square root of 2. Very good speak. So our ratio for the sides of a 45, 45, 90 triangle are always 1, 1, root 2. So let's say we had a triangle where this side was 4. Well, if this side was 4, then this side would be 4, okay? And all I'm doing is I'm applying a scale factor of 4. So if I have 4 times the square root of 2, well, I can just write that as 4 times root 2 or 4 root 2. So our proportions allow us to compare any triangle that has these measurements, 45, 45, 90, will have this ratio of its sides. Okay, now for this one, I'm going to help you out a little bit on this as well. I'm going to give you two sides, 1 and 2 for the hypotenuse. What's the missing side here? Pause the video, do the Pythagorean theorem, and find out, spoilers, it's the square root of 3. So the next ratio here is 1 root 3, 2. Please be careful on the order here. Sometimes I find people say, oh, well, 3 is a bigger number than 2. And so let's go 1, 2, root 3, and they'll call this the hypotenuse is root 3. Root 3 is smaller than 2. Okay, so it's a square root, right? Square root 4 is 2, so square root 3 must be less than 2. So this is our ratio. One thing that we'll talk about a lot when we talk about matching sides and the angles is, remember, an angle is like a camera lens, right? It opens up, and how open the lens is determines how big the picture you take is. Just like for an angle, if I open up 30-degree angle, the side across from it is going to be smaller than if I had opened up 60-degree angle, the side across from it, right? So small angle makes a small side opposite. Big angle, big side opposite. And that's why across from our right angle, the largest angle possible in a right angle triangle is the big side, which scientists have called the hypotenuse. All right, so when I talk about these triangles, the next thing that we'll see is this kind of table here that looks maybe a little scary, but let's make it make sense real quick here. So I'm going to draw out my 45, 45, 90 and my 30, 60, 90. Okay, and I'll put in what their values are here. So this will be our 45-degree angle, and it's a 1, 1, root 2. Remember those numbers. And so this is our 60-degree. This is our 30-degree. Okay, and that is a 1, 2, and root 3. Yeah, I did my words backwards. Whatever, right? I labeled the sides correctly. I'm happy with that. Of course, these are 90s. Won't waste your time. Okay, so when I'm looking at a trig ratio, remember I consider the angle that I'm looking at is the sort of my reference point. And then I'll go opposite over adjacent for tangent. Well, that's 1 over 1. Yeah, that's just 1. So tan 45 is 1 degree. This is kind of the test that we were always given to like make sure your calculator is in the right mode. If you're in degree, tan 45 equals 1. It's a nice thing to remember. Okay. The next angle the next ratio is sine of the same angle. So we're going to go opposite over hypotenuse. That's 1 divided by root 2. Another way you'll see this written is root 2 over 2. We'll learn how to change it so that the radical is not on the denominator. This is actually a really helpful way of writing it, and you'll see why, because it makes a pattern which we'll look at later. Cosine, of course, is just adjacent over hypotenuse, and so it's the same value as sine was. Looking at 30 degrees, okay, we've got opposite 1 over root 3, okay? Sine 1 over 2, cosine root 3 over 2. For 60 degrees, tan is root 3 over 1. And yes, I know it's below here. It's a paper, just move the paper. Sine of 60 degrees is root 3 over 2. Cosine of 60 degrees is 1 over 2. And these ratios, you don't have to memorize them because what you can do is you can just draw the triangles. There is the alternative that maybe you don't like drawing the triangles and you just want to memorize the ratios. I will kind of give you the combination of both in a little bit here. Save that thought because really, Math 20-1 teachers usually just say, hey, here are triangles. Remember triangles. I'll show you a 30-1 thing that might help you later. Before that, though, let's do a quick example. Actually, I'm going to skip this example. Just the idea here is that if you've got a ratio that you're going to be using, that ratio is like a scale factor. So if I have a 1 root 3 2 triangle that I want to compare to a something 4 triangle, all I do is multiply by a scale factor and I'll get the new proportions. That, by the way, is essentially the answer to the question. It's just condensed. All right. The next thing I can do is solve the ratio for any angle given a point on a Cartesian plane. And that's really handy, and it's something we're going to see come up a lot. So let's go ahead and we'll draw a terminal arm that passes through the point 4, -3. So that's here. Let's go here. Our point, let's draw this little point in black here, right here. That's the number 3 when I wanted to put 4, -3. So using this, if I have this kind of angle, use the reference angle, right? So the nearest x-axis. If I want to find the ratios for this angle, that doesn't mean I want to find the value of the angle. I just want to find tan theta, that angle, sine theta, and cos theta. And it's really nice when I've got a Cartesian plane if they give me this point because, well, I can very easily finish this triangle. I've got my x and my y values match with our coordinates. So I'm going 4 on our x-axis, and I'm going down 3, so -3 on my y-axis. And so that gives me the two sides, opposite and adjacent, of my triangle. To find my last side here, all I got to do is the Pythagorean theorem. This is a Pythagorean triple, so it's pretty easy to remember that. If not, or if I say algebraically determined, you should do the Pythagorean theorem. Use the Pythagorean theorem to find whatever the missing side is on this triangle. Okay, then it's easy. All I've got to do for tangent is I take opposite over adjacent. So opposite is -3 and adjacent is 4. Sine is opposite over hypotenuse, so that is -3 over 5. Keep in mind when you do the Pythagorean theorem, your hypotenuse always outputs as a positive. It is always positive. Don't mess with that. Just leave it as a positive. And then finally, adjacent over hypotenuse, this is equal to +4 over 5. Okay, so these are the trig ratios for this triangle. -3 over 4, -3 over 5, and 4 over 5. Cool beans. Now, the next idea here that we can use is that, well, we said this point was really helpful for us in labeling sort of our triangle out here. Why not, instead of using opposite and adjacent, if I'm always using reference angles, opposite is always y. right? So if I go over here, then opposite is my y value. If I go this way, opposite is still my y value. Adjacent is always my x value. And then finally, our hypotenuse, I'm going to use this letter, r. Any guesses on why we might use the letter r? Well, it goes back to when we were doing our standard position angles and we did rotations, right? We did rotations around. If I take this line and I rotate it all the way around my Cartesian plane, what do I form? A circle. And what is that line in relation to the circle? It's r, the radius. Aren't you thrilled to hear that? Okay, I think we're on our last rule. Yeah, then we'll maybe look at a couple of those. Okay, so one other really helpful way to think of our Cartesian plane for remembering this is that if I am using my x and y values, my ratios will have a pattern of when they're positive and when they're negative. So over here in quadrant 1, x is positive, y is positive, and our radius is always positive. So that means all of our ratios are going to be positive. Over here in quadrant 2, x is negative, y is positive, and our radius is always positive. So that means any ratio that uses x is going to be negative. And so when we talk about that, well, cosine and tangent both use this. Only sine is positive, okay? Over here, x is negative in quadrant 3, y is also negative in quadrant 3, our radius is always positive. So the only one that uses two negatives, tan, is positive. And then finally, over here, our x is positive, our y is negative, and our radius is positive. My r's look like v's, deal with it. The only match here where we have a positive, where the sign is matching, is our cosine ratio is positive. So in our quadrant 1, everything is positive, so all the ratios are positive. Then it's sine, tan, cosine. The way we remember this is the cast rule. A little bit nasty that you start in quadrant 4 instead of quadrant 1. But cast, if you go around the circle, you've got cast. And that helps remind us which ratios are positive and which are negative. That's really handy. Okay, what are the trigonometric ratios for an angle formed by a terminal arm going through the point -2, -3? I'm not even going to do a drawing here. I'll just help you out with this by saying x equals -2, y equals -3, r equals, well, let's do the Pythagorean theorem here. So I got -2 squared plus -3 squared equals r squared. So that's 4 plus 9 equals r squared, which means r is the root of 13. Notice that I'm going to leave this as the square root of 13. Also notice with these brackets, these squares, the negatives are going away. There is never going to be a negative radius, ever, ever, ever. It's always positive. So let's write our ratios here. Tangent of theta is always equal to y over x. So that's equal to -3 over -2, which is 3/2. -2, -3, that's in quadrant 3. Tangent is positive in quadrant 3. That matches with what we know. Sine theta is y over r, which is -3 over root 13. Nothing to simplify there. Cos theta is x over r, and that's -2 over root 13. There are our three ratios. Okay. And I kind of maybe glossed really quick over this. You had that from our example above, but this is helpful to remember. Alrighty, skipping those. So here's a nice way that I've found some people to help remember those special angles. So with the 45 degrees, 30 degrees, 60 degrees, what I'm going to do is I'm going to draw just one quadrant of our Cartesian plane. I'm drawing quadrant 1, and I'll draw this. So let's go. That'll be our 30, 45, 60. And I'll just write that up here because I can. Let's go 45, degrees, and let's go 30 degrees. Okay. And I'm also going to draw those special triangles over here. So that's pretty good. Sure. And I'm going to do one interesting thing. I'm going to make it so that for both of these, the hypotenuse is 1. So that essentially what I'm going to do is I'm going to take a line that has a length of 1, right? So I got this line here that goes from 0, 0 to 1, 0. Okay, and I'm going to rotate it all the way up here so that it goes to 0, 1. Okay, so what I'm doing is I'm making an arc. That's actually not the worst arc. That will go from 0 to 90 degrees. And at some point, it'll intersect this one length line. This ray with a length of 1 will intersect at all these points. And at each of those, it'll have like a little triangle that it makes. Okay, I'm not actually going to draw all the triangles. Okay. Actually, maybe I will later, but let's get there. So if I want to have this one line representing both triangles, that means I have to change my proportions. And in class, we might spend a little bit of time actually doing this, but for right now, I'll help you out. This is equal to 1 over root 2, right? So if I want to go from root 2 to 1, I have to divide by root 2. So this becomes 1 divided by root 2. Duh. And I told you already, there's another way we can write that. It's root 2 over 2. Root 2 over 2. Okay, for this one, it's a little easier. To go from 2 down to 1, I have to divide by 2. So 1 becomes 1 divided by 2, 1/2. And root 3 becomes root 3 divided by 2, which is what it is. There's nothing more to say there, I guess. So if this is our line, as I go through on my 30-degree angle, that point matches with our opposite being 1/2 and our adjacent being root 3 over 2. Okay, and so let's actually draw this out. So in other words, I've got this triangle here, right? Where if I go 30 degrees, if this line is 1 and I bring it up here, it'll go up to 1/2 at this point, and it'll still be going across root 3 over 2 because it matches this special triangle when it's 30 degrees. Okay, so what's this one going to be? What's the value of our point there? Well, it'll go to root 2 over 2 for both the x and the y. Remember, 45 degrees makes an isosceles triangle. That's how we say it. Very good speaking. And then finally, our 60 degree, when our arc or our ray is up to 60 degrees, subtend 60 degrees here, our point is going to be just the opposite of this, right? So now it's this angle. So it's root 3 over 2 is our opposite or our y value, and 1/2 is our x. And you might say, this is just worse. This is more confusing. I liked when we had triangles and we weren't screwing with them instead of making them a bunch of triangles. But let me try and convince you how this helped me memorize them a lot better. Look at a pattern here. Remember that y is our sine value, right? Sine theta, if our let's do this. Y over r is sine theta. If our radius is just 1, that means sine theta is just y divided by 1. And so for our sine ratio, all I've got to do is take my y value and plug it in. Watch this pattern. At 0 degrees, our y value is just 0. Then it goes 1/2, root 2/2, root 3/2 to 1. I like to think about this as saying, starts at empty, you go 1, 2, 3 to full. And that's kind of handy because it's just counting 1, 2, 3. Our x value matches with cosine, right? Remember, our radius is just 1, so we can ignore that. Dividing by 1, it's trivial. I start at full, 1, 3, 2, 1, empty. That I find to be a really helpful way to remember this. And so if you ask me what is sine of 45 degrees, I know it's the middle step, it's root 2 over 2. And to prove a point, I wasn't looking at the screen while I did this, and then I remembered you guys can't see me, so it wasn't very helpful. That's the first half of this. I'm going to leave it as halves so that we kind of hit the next two things afterwards. What you just saw here, you can kind of skip this. If it helps, use it. But all the rest of these notes here, that is all fair game for quizzes and tests. So hopefully you found this video helpful. I'll see you in the next one.